Hello, Count Sacke here, back with another GD Dynamics video. Today, we're tackling the second part of episode 6, where we calculate the terminal velocity of the player, and we'll also be deriving a function that can basically predict the path of a player falling from a ledge. So, to be able to understand this episode, you'll obviously need to watch part 1, episode 3, and episode 4. I would like to point out something that I missed from the previous episode. I do now believe that the mini-modes might actually have a different gravitational acceleration from their normal counterparts. So here's a table with the values. I'm actually quite unsure if I can say that the gravitational accelerations are the same or if they're slightly different. I'm unable to tell. Alright, with that, let's get things started. To understand the concept of terminal velocity, I'll have to talk about Newton's laws of motion very briefly. So the first law of motion states that when a net force on an object is zero, it doesn't accelerate. The second law of motion states that a non-zero net force on an object will accelerate it. Lastly, the third law of motion states that if you exert a force on an object, that same object will exert a force equal in magnitude, but in the opposite direction you're exerting at. Overall, Newton's famous equation F equals ma summarizes all his three laws.
But how can objects accelerate if the law of acceleration states that there's always an opposing force?
This is something that can baffle a lot of people. I know it used to baffle me a lot, but you have to keep in mind that the acceleration is caused by a net force, meaning the sum of all forces in a situation. For example, you're pushing a box, and we will neglect friction for now. The force you're exerting on the box is F sub 1, and by the law of interaction, the box also exerts a force in the opposite direction with the same magnitude as F sub 1. At this specific point where you're exerting a force, they would cancel out and become zero. But remember, there are other forces at play here, specifically you pushing against the ground to move forward. Sure, the ground pushes back up at you, but that is exactly what causes you to move forward, and hence allows for the net force to be non-zero, therefore acceleration is possible. Let's now consider frictional forces. I'll only focus on the concepts because the equations aren't actually needed for this episode. A frictional force depends on a few factors: the magnitude of the velocity propelling the object in a direction, and the surface area that is affected by the frictional force. Using the same example from before, but this time with friction, you might notice that there is a minimum amount of force needed to move the box. If you have a weaker force than that minimum, the box doesn't move. Once you exert the same amount of force as the minimum, the box moves, but with a constant velocity. Lastly, if you exceed the minimum, the box accelerates. With those concepts in mind, let's now tackle terminal velocity. Terminal velocity is the maximum velocity that something can reach in a fluid. The fluid exerts a frictional force in the opposite direction by the law of interaction. For an object falling, it would accelerate, and this would mean that the frictional forces from the fluid also increase in magnitude. However, since the gravitational force remains constant, at some point, the frictional and gravitational forces become equal and would cancel each other out, meaning you're left with a net force of zero, which also means that the object no longer accelerates and maintains a constant velocity. Let's now see how we can calculate the terminal velocity in GD. Given a position against time graph, we would just have to measure the slope of the line. However, in playtest mode, this path is not a position versus time graph. It is an x position versus y position graph, so we need a bit of algebra. In the previous part, we derived these two equations of motion. Luckily, we can actually use almost the same equations derived from last time. The first equation is t is equal to delta s sub x divided by v sub x. For the second equation, all we need to do is look at the y component of displacement. Since the object would have reached terminal velocity, the acceleration would be zero. So, after doing some algebra, we find that the terminal velocity is equal to delta s sub y divided by t. Substituting the first equation into the one we just derived interestingly tells us that we don't actually need to use the relative scale formula to convert pixels to blocks. Of the 7 modes, the cube, ship, UFO, and robot are the only ones that have a terminal velocity, but we need to take into account the mini-modes for them. The spider and ball appear to have no terminal velocity and fall according to the displacement equation. For the wave, it doesn't accelerate due to gravity. Really, it doesn't. So, here's my methodology. To be able to calculate the terminal velocity, you use the same setup from the previous part, go into playtest mode and let the path be drawn out. You want to measure the path of the line that is specifically linear. Finally, measure the height and the length, then plug it into the formula. So here are my values for the terminal velocities. When looking at the terminal velocities of the objects, it is clear that for the cube and robot, their mini and normal versions should have about the same value. For the ship and UFO, the mini versions have a larger value than the normal ones, which makes sense. I'll now proceed to make a piecewise function to approximate the displacement of the modes at different speeds. So first off, a piecewise graph is a function that has multiple functions, but depending on certain conditions, only one of those functions will be executed. Here is a simple example of a piecewise function. The way to understand this is that when the x is greater than 0, the f of x will output x squared, but if x is less than or equal to 0, it outputs negative x. Now to make our displacement function, let's recall the displacement equation. Delta s is equal to at squared divided by 2 plus vit. Now we only want to input a single value into the function, and well, this function is a function of time. But as I mentioned earlier, a graph of position versus time is different from a graph of y position versus x position. So we need to be able to convert this displacement equation to be dependent on the x position. Luckily, we already know that t is equal to delta s sub x divided by v sub x. And what's great is that it's with respect to the x position, so even better. Rather than plugging this into the equation, I'll just leave it as t, but just remember that this is what t is. We have a pretty accurate displacement function for when the object is accelerating, but this doesn't take into account the terminal velocity and becomes very different after some point. We know that after some amount of time, the player reaches terminal velocity. When the time passed is before that time, we use a displacement equation, but after, we use this equation. S is equal to Vy max, or the terminal velocity, times t. However, we need to know what value of t to use. So to do that, we can use the equations of motion. Specifically, delta v is equal to at. We can focus on the y component, and we know that delta v sub y is equal to negative gt. It's specifically negative because we're only focusing on when the object is going down, but I can guarantee you that because geometry dash you can go up, it can also be positive. So if you actually were to split delta v sub y, you know that the initial velocity is equal to 0 because we fall off a ledge, so it starts at 0 velocity. And with that, we find that t is equal to the negative terminal velocity divided by gravity. With that, here are the displacement functions that approximate the displacement of a player. So we've completed the episode on gravity. In this part we talked about the terminal velocity and derived a displacement function that approximates the path of the player as they fall from a ledge. This has been quite a fun episode to do, and that's really about it for now, so thanks for watching and hope you've enjoyed.